This is my lab report for Lab 3, Black Holes and Orbits. For this lab, we found the mass of a black hole and orbited a spaceship around a moon and a planet without crashing. We used code to create the model for both of these. The main physics principle I used for this lab was Newton's second law, force equals mass times acceleration. The first thing we did was finding a mass of a black hole. This is the video of the model I created. The yellow ball is the star, the black ball is the black hole, and the orange arrow represents FNet, the blue arrow represents the perpendicular FNet, and the pink arrow represents the parallel FNet. The average mass of the black hole I found was 1.425 e to the 34 kilograms. What does this mean? We were told to discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. The net force is the cause of the motion. It's all the external forces added up. The rate of change of momentum is the resulting effect on the object from the net force. It is what happens because of the net force. The net force parallel component changes the speed of the object, while the perpendicular component changes the direction of the momentum. The second part of this lab was called Orbit and Don't Crash. This is the model I created for the second part. As you can see, the blue ball represents the planet, the cyan ball represents the moon, and the pink ball represents the spaceship. The ship was supposed to orbit both the planet and the moon, and the speeds I chose for the x component was -135, and for the y component I chose 0 for the speed. I'll replay the video. As you can see, the spaceship does go all the way around the moon, and then it continues to go around the planet. And the pink line represents the travel path by the spaceship. So, what if? The next question was this imaginary system has a black hole, a star, a planet, and a moon. If you wanted to predict the motion of the entire system, what would you need to include in your computational model? Think about all the interactions in the system. Would there be any dominant interactions, or would all of them contribute the same or more or less equally? To do the model, I would need to include everything in the system because they all play a factor on each other. For how much they contribute, each thing would contribute depending on the size, the mass, and the distance from each other. That is the end of my lab report.